Your electric bill is one of the most predictable expenses in your life. It shows up every month. It goes up a little every year. And for most people, there is nothing you can do about it except pay it. What I am about to tell you challenges that assumption. But I'm going to be more careful with the numbers than most of the coverage you've seen on this, because the honest version of this story is still a big deal. It just isn't the version most videos are telling you. A Chinese company has built a battery that, cell for cell, already costs meaningfully less to manufacture than the battery sitting inside your current home storage system. Or the one you'd buy today if you wanted one. Not half the price. Not yet. But real, verified, and moving in a direction that matters a lot over the next 2 to 3 years. I'll give you the actual number in a minute, and I'll tell you exactly why it matters, even though it isn't as dramatic as the headline version. The company is CATL. They are the largest battery manufacturer in the world. You've probably never heard of them by name. But if you drive an EV or own a home battery from almost any major brand, there's a real chance their cells are already inside your system right now. This is the same company that supplies cells to BMW, Volkswagen, Mercedes, Hyundai, Toyota, and Tesla. Their new battery is called Naxtra. It runs on a completely different chemistry than anything currently inside a Tesla Powerwall, a Tesla vehicle, or almost any home battery sold in Western markets today. And the reason Tesla can't simply copy this and match the price isn't about patents, and it isn't about politics. It's structural. I'll walk you through exactly what that means in a few minutes, because once you understand it, this whole story clicks into place differently. Here's what you'll know by the end of this video: the real, verified cost gap between this chemistry and what you'd pay for equivalent storage today. Not the exaggerated version. The specific reason this is cheaper at all is down to the raw materials. The honest, structural reason Tesla is not positioned to match this in the near term. A real timeline for when this could actually reach Western consumers. And the limitations. What this battery genuinely cannot do yet. Because I'm not going to give you only the exciting half of this story. Before I get into any of that, drop your current monthly electric bill in the comments. Just the number. By the end of this video, you'll understand exactly what would need to happen to storage economics for that number to eventually move. And roughly on what timeline. I read every comment on this channel personally. And if this is your first Iron Circuit video, hit subscribe now. This channel finds the technology shifts that are about to change what you pay for energy and tech before mainstream coverage picks it up and gets half the story wrong. This is one of those stories. Let's get into it. Let's talk about your money first, because that's the part most videos skip past to get to the flashy chemistry talk. The average American household uses around 10,000 kilowatt hours of electricity a year. At the average US residential rate of roughly 17 cents per kilowatt hour, that's somewhere close to $1,400 to $1,600 a year in electricity. And that number has been climbing, with rates up roughly 7% over the past year, according to federal energy data. Home battery storage is supposed to help with that. Charge cheap overnight, use stored power during expensive peak hours. Time of use plans in places like California and parts of the Northeast already let homeowners with any kind of battery save real money, commonly $1,000 to $2,400 a year. The problem is the upfront cost. A Tesla Powerwall 3, fully installed, runs somewhere between $13,000 and $16,000 in 2026 for 13.5 kilowatt hours of storage. That works out to roughly $900 to $1,000 per kilowatt hour of installed capacity, which includes the cells, the pack, the inverter, and labor. At that price, payback stretches into the 10 to 15 year range for most households. Hard to justify. Now here's where I need to slow down and be precise, because this is the part almost every video on this topic gets wrong. CATL's raw sodium-ion cell materials run somewhere around $10 to $19 per kilowatt hour. That's just the ingredients, not a finished cell. At the finished cell level, third-party analysts and battery researchers currently put sodium-ion costs somewhere around $46 to $70 per kilowatt hour, depending on design. Separately, Haina Battery's general manager told Chinese media in April 2026 that current sodium-ion prices are running $69 to $97 per kilowatt hour at the cell level. Above today's lithium prices, not below them. Compare that to today's cheapest lithium chemistry, lithium iron phosphate, or LFP. The same chemistry inside most home batteries, including the Powerwall 3. LFP has crashed in price over the past 2 years due to oversupply and is currently sitting around $50 to $55 per kilowatt hour at the cell level. So at the cell level, the only fair comparison, sodium ion's advantage over today's cheapest lithium isn't 50%. Right now, in mid-2026, it's closer to 0 to 20%, and by some estimates, sodium ion isn't cheaper at all yet. That's the real, verified, apples to apples gap. I'm not going to tell you it's smaller than that, just to sound careful, and I'm not going to inflate it, just to sound exciting either. Here's why this is still a big story, despite that thin current gap. It's about where the trend line is heading, not where the price sits this exact month. As sodium-ion production scales from tens of gigawatt hours a year toward 200 or more by 2028, multiple industry forecasts expect cell costs to fall toward $40 to $55 per kilowatt hour, while lithium carbonate, which hit $20,000 per ton in January 2026 after repeated spikes, stays exposed to the same volatility it's always had. 85% of the world's lithium supply sits in just 3 countries: Australia, Chile, and China. Sodium carbonate, by comparison, costs around $200 per ton, and the raw material is in seawater and table salt. That's not a supply risk in the same universe. Translate that forward to your actual bill. It doesn't mean a fixed percentage cut on your electricity rate. No verified study makes that direct connection yet, and I'd be skeptical of any video that gives you one. What it does mean is that as cell costs fall, the installed cost of a home battery system falls with it, which changes the payback math, which changes how many households can realistically justify installing storage at all. If installed system costs eventually track cell costs the way they have with lithium, a system equivalent to today's Powerwall could plausibly land at $5,000 or below at scale, which would cut the payback window to 5 years or fewer for a lot of homes. That's the shift worth watching, not a battery that's already dramatically cheaper today. Your current lithium-ion battery, phone, car, home system, moves lithium ions between 2 electrodes when it charges and discharges. Lithium works well because it's light and energy dense, and the industry has had 50 years to optimize it. The problem is where it comes from and what it costs to get there, which we just covered. Sodium-ion swaps lithium for sodium, one element to the left on the periodic table. It behaves similarly enough that most of the battery architecture carries over, and it removes the lithium price volatility problem almost entirely. There's a second, less obvious cost advantage. Lithium-ion needs copper foil on the anode because lithium reacts badly with aluminum in that position. Copper is expensive, and its price swings with global demand too. Sodium doesn't have that restriction. You can use cheap aluminum on both electrodes. CATL says this design also cuts the anode's volume by roughly 60% compared to a standard LFP battery. Strip out copper, and you've removed one of the more expensive, more geopolitically exposed materials in the whole supply chain. CATL's Naxtra hits an energy density of around 175 watt-hours per kilogram, competitive with mainstream LFP cells used in home storage and entry-level EVs, though well short of the 250-plus watt-hours per kilogram in the high-performance nickel-based cells used in long-range vehicles. It supports up to 10,000 charge cycles by CATL's claim, operates from -40 to +70 degrees Celsius, and can fast charge from 30 to 80% in 30 minutes, even at -30 degrees. A condition where most lithium batteries either refuse to fast charge or damage themselves trying. Researchers at RWTH Aachen University in Germany published an independent assessment in a cell press journal in 2026 comparing Chinese sodium-ion cells from Haina Battery, a company closely related to CATL's approach, against Tesla's build quality. Their finding: the sodium-ion cells matched most performance parameters and production quality standards found in Tesla's best lithium-ion cells. That's an independent, peer-reviewed signal, not a company press release. And it's worth verifying the exact quote and journal citation before this line goes into a final cut, since it's doing real credibility work in the script. Chang'an, a major Chinese automaker, is already selling a car called the Nivo A06 with a 45 kilowatt-hour Naxtra pack from CATL. At current cell costs, that pack is worth somewhere between roughly $1,800 and $3,500. A real, drivable number, not a lab curiosity. Range is around 250 miles, with the same fast charge and cold weather performance described above. Now here's the part that actually surprised me, because the reason Tesla hasn't matched this isn't the reason most videos assume. It's not that Tesla lacks the engineering talent, and it's not that CATL is hiding some patent wall. Tesla is already a CATL customer. CATL supplies cells that go directly into Tesla vehicles today. If CATL scales sodium-ion the way it's promising, nothing is stopping Tesla from buying those cells too, the same way it buys lithium cells now. LG, another Tesla supplier running the Model Y and Model 3 line in Nanjing, has already announced its own sodium-ion pilot at that exact factory. So why hasn't Tesla switched? 3 real structural reasons. And this is the deeper version of that answer. First, scale lock-in. Tesla has invested over $10 billion in lithium-ion manufacturing infrastructure across gigafactories in Nevada, Texas, Germany, and Shanghai. Every machine, electrode coating lines, cell formation equipment, quality control systems, is calibrated for lithium chemistry. Switching to sodium ion isn't a software update. It means replacing physical equipment, requalifying every process, and rebuilding supplier relationships from the ground up. Second, supply contracts. Tesla is locked into long-term lithium agreements with Piedmont Lithium in North Carolina, Liontown Resources in Australia, and others. Multi-year deals with real financial commitments on both sides. You don't exit those cheaply or quickly. Third, hard carbon. Sodium-ion batteries need hard carbon anodes instead of the graphite used in lithium-ion batteries. Hard carbon comes from agricultural waste, coconut shells, corn stover, through a specific high-temperature process, and China currently controls most of the world's production and processing infrastructure for it. Building a competitive hard carbon supply chain outside China takes years and serious capital. Tesla has not announced a program to do this. And underneath all three of those is the simplest reason of all. As long as LFP keeps getting cheaper through oversupply, the financial case for Tesla to switch weakens every quarter that lithium prices stay soft. The moment lithium spikes again, and it already has once this year, that calculation flips fast. Tesla's own suppliers are already building sodium-ion capacity, and that the real barrier is manufacturing lock-in and supply contracts, not some technology wall, is exactly the kind of detail Iron Circuit tries to find before it becomes something everyone's arguing about online 6 months from now. If you want that kind of analysis on every major energy and tech story as it breaks, subscribe and turn on notifications. That's the only ask here. Energy density. At around 175 watt-hours per kilogram, Naxtra is fine for home storage and short-range EVs, but well, short of the 250 plus watt-hours per kilogram in Tesla's long-range cells. If you want maximum driving range, sodium-ion isn't the answer yet. Cycle life. Some sodium-ion designs on the market are currently rated around 3,000 to 5,000 cycles versus 6,000 to 10,000 for mature LFP cells. CATL claims 10,000 cycles for Naxtra specifically, but that figure hasn't been independently confirmed on cars actually on the road yet. Treat it as a claim, not a fact, until it is. No direct bill translation. There's no verified study directly converting sodium-ion cell costs into a specific percentage cut on anyone's electricity bill. That connection doesn't exist in the data yet. What's real is the effect on installed system cost and payback period, which we already covered, not a shortcut fixed percentage number. Trade and market access. CATL's chief scientist confirmed in late May 2026 that manufacturing bottlenecks are resolved and mass production is underway in China. But mass production in China isn't the same as mass availability in the US or Europe. CATL is also on the US Department of Defense's list of companies subject to trade restrictions, effective 2027, which doesn't stop consumers from buying products with CATL cells inside them today, but creates real uncertainty for Western companies wanting to build products around this technology. Getting sodium-ion home batteries into American homes at scale needs either CATL navigating around those restrictions, a Western company licensing the tech and building its own supply chain, or a domestic alternative. And General Motors has already announced a sodium-ion R&D push for grid storage with a startup called Peak Energy, though R&D programs and shelf-ready products are years apart. Safety and cold weather performance. A genuine, verified advantage. This one's real, not just marketing. Sodium-ion cells have a thermal runaway onset measured at roughly 30 to 50 degrees Celsius higher than lithium chemistries, meaningfully harder to push into a fire risk state. CATL claims around 90% usable capacity at negative 40 degrees Celsius, which lithium packs can't match without heavy, expensive heating systems. If you live somewhere with brutal winters, that's a real physical edge. If sodium-ion scales the way CATL's roadmap suggests, reaching cost parity with LFP by 2027 or 2028 and continuing below it, the economics of home solar plus storage shift meaningfully. It doesn't just compete with lithium in one product category. It decouples a large share of battery manufacturing from a resource controlled by a handful of countries and prone to price shocks. Grid-scale storage operators, utilities stabilizing renewable power, and countries with zero domestic lithium all suddenly have a cheaper, more stable option for large-scale storage. That shift doesn't just affect individual households. It changes who holds leverage in energy. Right now, utility companies hold that leverage because generating and storing power at home is too expensive for most people. When storage gets cheap enough, that balance shifts. The utility becomes a backup instead of a necessity. That has real implications for energy companies, grid operators, and the economics of natural gas peaking plants over the next decade. None of that happens because of one battery in one Chinese sedan or one home battery pilot. It happens only if this cost curve keeps bending the way CATL says it will, quarter after quarter, at a scale nobody outside China has proven yet. That if is exactly why this is worth watching closely instead of writing it off as either hype or a done deal. So here's the honest question I want your take on. If a battery like this is already rolling off production lines at scale in China, is the thing actually keeping it out of your home or your driveway, the technology itself? Or is it trade policy, tariffs, and supply chain politics that have nothing to do with whether the battery works? Two completely different problems, two completely different solutions. I want to see that exact debate in the replies. If you want to be the person who understood this shift in energy economics before it ever showed up in a headline about your utility bill, Iron Circuit is the channel that gets you there first. Subscribe now and turn on notifications so you don't miss the next one. Because the next video covers what happens when this same sodium-ion cost curve collides with the residential solar market. And the number that comes out of that combination should genuinely worry every energy company currently operating in the West. You do not want to miss that one.